maybe the initial goal of the project doesn't work for whatever reason, but you can often kind of like pivot away from it. And so you can kind of use the ideas or the insights you had. So like, well, I thought I was addressing this question, but actually there's another question nearby that, I thought about and I can maybe reuse the pieces I had. So trying to salvage pieces from like, something that didn't initially work is often very fruitful.
The guest of today's podcast is Dr. Jonathan Heckman. He is a theoretical physicist at University of Pennsylvania and works on generalized symmetries, the Swampland program, holography, and F-theory among other related areas. So let's welcome Dr. Heckman to the podcast and listen to what he has to say. So first of all, Dr. Heckman, welcome to the podcast. Nice to have you.
Thanks for having me. Yeah.
So before we talk about anything else, can you tell us a bit about the projects that you are working on nowadays?
Well, there's a bunch of them, and they're all on different topics. So, I would say one general thing I'm working on is indeed things connected with generalized symmetries, but in particular, questions having to do with what happens to generalized symmetries when you couple a system to gravity. So there's this general lore that in gravity, we don't have global symmetries. And so the question is what becomes of them? Do they get gauged? Do they get broken? And so what we're trying to do in many of these projects is understand better what's happening with those symmetries. So that's one kind of general set of papers, I would say, or set of projects that are kind of in various stages of uh, gestation. Another thing has to do with just generalized symmetries in its own right in quantum field theory, just understanding how it works in many different settings, trying to come up with more kind of concrete realizations of certain kind of abstract categorical symmetries. Like, can you write down Lagrangians for some of them? That's another general theme. Um, yeah, lots of projects. I would say another kind of theme that we're exploring is that I'm exploring with people is aspects of the Swampland program, what kinds of branes you have in those systems, non-supersymmetric. What can you say about kind of their dynamics and properties? And another kind of general question we're looking at is just more broadly, what sorts of quantum field theories can be realized in the context of, say, uh, quantum gravity? So is it every kind of quantum field theory, or are there limitations in terms of the kinds of quantum field theories? And kind of the implications of constructing such quantum field theories for, let's say you have an experiment and they find one of these kind of more exotic types of quantum field theories. What would it mean for kind of string theory and quantum gravity? So um, I'm sure there's other projects I'm forgetting. So apologies to my collaborators, but that's some kind of list of things I'm thinking about right now. Uh, yeah.
So when you say that you are studying the fate of generalized symmetries when you couple systems to gravity, so
Yeah.
do you mean gravity like a low energy gravity, or do you mean like string theory, like quantum gravity?
Honestly, both. Of course, like string theory, if you come in from that point of view, it automatically kind of tells you that you shouldn't be expecting global symmetries. But the way that that happens is in many cases kind of subtle because global symmetries, for example, can kind of emerge at long distances. So at short distances, you may not have a global symmetry, but as you start taking a limit where gravity is decoupled, then you can start to see it emerge. So I think it's fruitful to kind of explore it both from, if you like, a top-down point of view, using like an explicit string theory background, but then also kind of more from like a bottom-up point of view. Both in the context of, say, just low energy effective field theories, asking it that way, but also in the context of, say, holography, and in particular things like ADS CFT correspondence, where you don't necessarily commit to a particular, say, UV completion of the setup. So in those kinds of situations, you can again, uh, ask it, and there's usually some interplay between the two, I should say. So it's not like it's one or the other. But I think it's helpful to kind of pose it in both ways because if you're doing it from kind of a purely top-down point of view, then of course the question will be, well, how general is this? Did you just pick your favorite model, and what if I did it more generally? And bottom-up kind of considerations can help with that. And at the same time, bottom-up considerations can also kind of point to saying, well, is this a kind of universal feature, or did you have to assume extra structures in order to make it so? So that's why I think it's helpful to kind of do it in both kind of directions.
I
Yeah.
see. So I want to talk about some of the works that you have done in the past. So you did a lot of stuff, and you are still doing stuff, on F theory,
Uh-huh.
and specifically what I mean, one of the things that you did was to, make gut models out of F theory. So for
Yeah.
the audience, can you tell us a bit about what are gut models and why is F theory so useful to, for phenomenological purposes?
Right. Okay. So what is a gut? It's short for grand unified theory. And so the main idea is we already have examples of, unification of forces. That's been kind of a dominant theme in much of physics for stretching back for now centuries, I would say. So as a good example, electricity and magnetism turned out to be part of the same, theory. They're governed by Maxwell's equations. Kind of fast forwarding into kind of the standard model, we now know that kind of the weak force and electromagnetic force that kind of unify into this electroweak theory. And so, in fact, the kind of earliest examples of grand unified theory, so the original one proposed by George and Glashow asked, well, why aren't we just taking all the forces that we know about from the standard model and trying to package them together in terms of one kind of big universal force? And so, how could this be true? It can't be true at long distances because obviously we see the forces behaving differently. But their interesting idea was that, well, just like in the electroweak interactions, at long distances they appear to behave differently. As you start going to shorter distance scales, so above what we would call the scale of symmetry breaking, um, it looks like these forces are partially unifying. And so they just took that theme even further to write down kind of the first example of what we would call a grand unified theory, which we call in more technical terms, what they wrote down is kind of a non-supersymmetric SU5 gut. I mean, there were problems with that theory. One of the kind of striking predictions of the model is that it provides a kind of expectation that you should have, for example, baryon number violation, so protons should decay. And in fact, they decay too quickly in the original George I. Glashow model. There's other kind of intriguing things you can do. So, for example, there's this process of looking at renormalization group flows where you look at the strength of forces and you start asking what happens to the strength of those couplings as you start going to shorter and shorter distance scales. And if you look at those, then it turns out that the coupling constants of, say, the standard model look like they're going to roughly meet. They don't actually exactly meet in the non-supersymmetric SU5 gut, but it gets close. So that was all kind of the early stuff and in guts. And in I think it was appreciated pretty quickly that in the context of, say, supersymmetric models, that the unification, for example, gets better. So, for example, the scale of unification gets pushed up, so there's not as much of a problem with proton decay in some of these models. And also at the same time, the actual place where the couplings unify, it becomes a little bit sharper, that they start to come together more tightly. And so for all those reasons, this is not evidence of supersymmetry, but it's kind of, circumstantially, compelling that this thing starts happening in a supersymmetric model. And of course, there's issues with it when you start going to, say, higher loop orders, what the specific masses of the superpartners is. But it's at least very kind of attractive, from an aesthetic point of view, that things start to work better if you combine this, attractive idea of unification with now supersymmetry. So that's all at the level of what we would refer to as quantum field theory, nothing to do with string theory. And so kind of the early string theory models had this interesting property. So the ones from, say, that were kind of heavily studied in the 1980s, the so-called heterotic strings had this property that you could kind of naturally get these grand unified groups and structures to come out. And they didn't really start with, say, SU5 or SO10, but rather kind of even bigger groups. So there's kind of a finite list of what we call the exceptional groups. And the biggest of those is what we call E8. And so the interesting thing about the heterotic string is it provides a way of talking about this big E8 gauge theory coupled to gravity. And so then a lot of intense effort was developed in the 80s to understand what happens to these kind of E8 models as you start going down to kind of lower energies. And you can kind of embed many of the structures of the kind of four-dimensional grand unified theories into this bigger 10-dimensional framework now with E8 gauge theory. So that's all from like the 1980s. Um, but there are kind of questions you could ask about, like, well, how generic are these kinds of models? Are there other ways of kind of talking about, say, the standard model and building interesting quantum field theories that don't necessarily have these unified structures? And so roughly, I would say in the Okay, I don't know the history that well, but I would say in the kind of later 1990s into like the early 2000s, another kind of very kind of general way of building interesting quantum field theories coupled to gravity was through what we would call intersecting brane models. And here the picture is a little bit different. The idea, so in heterotic models, all the excitations are coming from what we would call closed strings. So ones that don't have endpoints, but instead just make closed loops. And in intersecting brane models, instead, all the particle content is coming from open strings that are kind of stretched between fluctuating d-branes. And so this is a very nice way to kind of flexibly build a huge number of models that actually look pretty close to that have standard model-like properties. And so the interesting thing is that the standard model field content is usually in what we would call low dimensional representations. And so you kind of can naturally accommodate all of this stuff involving the standard model. Okay, so off on this tangent. So then what is going on in the context of kind of F theory and what does it do? Well, the thing that intersecting brane models did very well was to kind of build you interesting quantum field theories, but they don't necessarily accommodate unification that well. So in particular, some of these structures like exceptional gauge groups that are very prevalent in heterotic models don't show up so easily in these intersecting brane models. And so the question became, well, do you basically just have to choose, or are these just different ranges of parameter space and so on? And and I should say that my colleagues at Penn, uh, Bert Everett, Ron Donaghy, and Tony Pantev in particular worked very heavily on kind of, I would say, the modern versions of uh, the heterotic side of the story and really kind of getting it into the most realistic settings. And then on the intersecting brane models side, my colleague Miriam Svedich did much of the kind of foundational work and also many of the more realistic intersecting brane models. And so there was all these different ways of putting things together, but it didn't necessarily mean that you kind of have an intersecting brane model which would kind of accommodate kind of the structures of grand unification. And so that's where kind of M theory and F theory come into the story because they kind of blend between the two, if you like. And the reason they do that is because they're not necessarily it's a perturbative string coupling. They rather kind of exist at strong coupling. And as a result of that, kind of more interesting kind of bound states of strings can form, and you can get more kinds of structures. So things that are just inaccessible at kind of these weak values of the string coupling. So kind of I think one of the big insights from kind of the M theory and F theory sides of the story is that you can actually accommodate both this intersecting branes type picture, but at the same time have these exceptional structures, these exceptional gauge group structures that seem to be very helpful in terms of getting grand unified structures as well. And I should say also the M theory stuff was developed quite a bit by like Bobby Acharya, Ed Witten, and Gordy Kane really kind of Gordy Kane in particular kind of and Bobby like looked very much at the kind of phenomenology of these models. And so F theory was, if you like, kind of the latecomer to the game in terms of people trying to. I mean, people knew that F theory would have like a lot of different kinds of interesting vacua. So in fact, the biggest landscapes we know about come from F theory. But somehow, kind of putting all the tools together to kind of build explicit grand unified theories was not something people had looked at. And I think part of it, I remember when we were first working on it, one of the people who worked on heterotic models said, well, why would you bother with this? Uh, there's a heterotic F theory duality. So anything you're going to say about F theory will just have a dual description in heterotic. So what's the use of this? But I think the point is that F theory is, at least the way we understand it now, provides you with a much uh, broader set of possible vacua in certain settings. Um, and so you basically borrow many of the kind of formal structures you see in the heterotic world, but you can kind of enlarge it to this F theory setting. And from that point of view, I would actually say that, calling it F theory, heterotic, or whatever is a bit of a misnomer. It's more just what corner of kind of vacua you happen to be landing in. And maybe there's a better description in terms of one or the other, but it's more that there's a big generic class of values for the moduli that you could be talking about. And it happens that this is a flexible way to start building interesting grand unified theories coupled to gravity. Uh,
Right.
so so I don't know if that answers your question, but that's
It
yeah.
does to some extent. So the thing is that to build standard model, I mean, you need particles that are chiral, right? So
Yeah.
can you build, theories with chiral matter in them using brane intersection models?
Oh yeah, yeah, that's definitely possible. Yes. And so the way that that comes about is there's two ways of doing it. So it depends on whether you're doing it in type 2B or in type 2A. Those are kind of the two classic places where people have tried to do intersecting brain models. So in type 2B, it's perhaps a little bit I find it at least a little bit easier to visualize. The reason is that what you do is you get let's say a higher dimensional Dirac field. So not necessarily one that's in 4 dimensions, but say in 6 dimensions or maybe something even higher. But then the point is that these intersecting brain models don't just have, the open strings coming from, degrees of freedom stuck at, the intersection locus, which is, say, over 6 dimensions, but they also couple to all of the higher dimensional gauge fields and other excitations of the brains. And so if you start switching on kind of background gauge fields for these brains, you can look at what happens to the zero mode spectrum. So in other words, the massless degrees of freedom. And as a result of switching on this background flux, you basically just via the kind of celebrated index theorems, you know that that there's going to be a mismatch in 4 dimensions now between the number of massless left chiral states and the right chiral states. And so that's one way to kind of see that you can definitely get chiral matter out from these kinds of settings. The kind of 2A version of this, which is obviously there's a dual description of the many of these things, and there's a 2A version of it. In the 2A world, it's instead kind of just due to the kind of way that the GSO projection works on kind of string theory degrees of freedom. So that once you impose GSO, which you have to do anyway to have a consistent model, it turns out that if the intersection locus is sufficiently localized, that it will produce chiral matter. And you can kind of go back and forth between the two pictures to see that you're kind of doing the same thing. So yeah, so for sure you can have chiral matter. And I think that was one of the things that people were very excited about, especially with the heterotic models back in the 80s, which is it was kind of the first kind of way you could imagine unifying chiral, quantum field theories with gravity in in a self-consistent way. So I think that so the intersecting brain models is again from that point of view just following in that kind of theme of how do we get chiral matter coupled to gravity in a consistent way?
Right.
Yeah.
So when you look at the techniques that people use for F theory, I mean, it has a lot of jargon like divisors and curves. So that all comes from algebraic geometry. So I
Yeah.
wanted to ask you that what kind of techniques from algebraic geometry are used for F theory analysis?
Um, well, you mean more specifically, like what are the, actual
Mhm.
techniques or?
Yes.
Okay.
Techniques or topics. Mostly, I wanted to talk about. So, what I want to ask you is that what kind of background in algebraic geometry one needs to have in order to work on F theory?
Oh, I see. Okay. So, I would say that in terms of, background in algebraic. Okay. So if you're an algebraic geometer, one of the first things you want to know about is what is kind of the ground field that you're working over. So they typically they're basically solving like, different kinds of interesting, polynomial, equations and things like this. That's kind of a very, you know, crude way of characterizing it. But one of the things you want to know about is what is the ground field that you work over. And so in this context, we're talking about working over the basically the ground field being the complex numbers. So not over the reals, but over the complex numbers. And there's a whole branch of algebraic geometry where you don't do that. You work over either characteristic P or mixed characteristic. That's not what's going on in this. And then specifically, the kinds of objects that you're typically dealing with are Calabi-Yau manifolds. So these are ones that have a vanishing first Chern class. So in algebraic geometry terms, it means that the canonical class is trivial. So that's kind of the technical side of it. And it's not just any Calabi-Yau, it's what we would call an elliptically fibered Calabi-Yau. So it's a specific kind of Calabi-Yau where uh, basically you can think about it as there's some base Kähler manifold, and then over that there is then a corresponding elliptic fiber. So for every point on this base, you then decorate it by this elliptic curve. And there's basically a holomorphically varying family of these elliptic curves. And so you have to know about things like Weierstrass models, minimal Weierstrass models, and how those kind of build you interesting elliptic Calabi-Yaus. Um, a general thing that happens, or the kind of where all the interesting physics is residing, is in the presence of having singularities in the elliptic vibration. So if everything was kind of a smooth elliptic vibration, I mean mathematically kind of the cleanest and tamest version of the story. But actually, many of the interesting features that you want for physics typically require, or they do require you to have singularities of various kinds. So, for example, the lift of the intersecting branes model requires a particular kind of singular elliptic fibration, and it takes place over the base in a complex codimension one subspace. And then the intersections are further degenerations where the singularities get even worse. So you have intersections, and then you have basically Yukawa couplings or interactions between all the matter fields. That happens even over even further degenerations. So these kinds of singularities start coming in when you start going to or have to be dealt with in this setting. And then so then that's kind of the geometric object you have to face. And then the way that algebraic geometers know how to deal with it is through a procedure known as blowing up or a blow up procedures. So this is basically where you kind of take the original singular manifold and you kind of delete it or you replace it by something that kind of smooths it out right at where the singularity is located. And then the structure of that blow up it often dictates precisely what's happening with the physics. And so that's some of the algebraic geometry side of the story that one has to just basically use. There's many things involving kind of understanding, you know, the moduli space of deformations, both blowups and also kind of smoothing deformations, things like this. In particular, obstructions to that. Those are kind of what I just described is kind of what we would call the kind of closed string perspective for F theory. There's a whole other kind of way that algebraic geometry enters, which is, I would say, kind of understanding more the gauge theory dynamics on the branes themselves. And kind of the simplest and cleanest version of that is through a particular gauge theory system known as like what's called the Hitchin system. So this is a gauge theory you define on kind of a complex curve, and then you study kind of the vacuum solutions to that. And that turns out to dictate what's going on in the elliptically fibered Calabi-Yau space. Um, there's generalizations of that Hitchin system to not just having, say, a complex curve, but instead having, say, a complex surface. What's the gauge theory on that? And there's this very, very rich interplay then between the kind of gauge theory you define over this particular, complex surface or curve and so on, and what you did in terms of the singular elliptic Calabi-Yau and how it got either smoothed out or deformed in some way. So that's, I think, yeah. So that's another kind of way that algebraic geometry kind of enters the game. I'm sure I'm forgetting some
Right.
of the pieces, but yeah, that's part of what I mainly worked on for
Mhm.
F3 stuff. Yeah.
So you said that singularities determine the physics. So by that you mean the singularities determine gauge groups, or do they also determine something else apart from gauge groups?
Yeah, so the basic version of what is now known as kind of geometric engineering is
Hmm.
that first of all, the singularities tell you the groups, but not just that, they also tell you about if the singularity kind of gets worse at places on further degeneration loci, then it actually tells you about matter. And if it gets even worse, then it can tell you about interactions between the matter. So I don't know. Can I use a whiteboard to draw anything, or is it?
No, no, it's fine. You don't have to. I think I just want to know the
Okay.
basic idea that do the singularities also determine something else apart from gauge
Yeah, yeah,
groups?
yeah. So it's not just the gauge groups. It's actually telling you quite a bit more. It tells you about the matter content that you have, and also the interactions. And uh, yeah,
You also referred to the blow-up procedure. So if you have one singularity, there can be more than one resolutions of those singularities. So,
right.
right. So do different blow-up procedures lead to different physics? And what kind of?
Yeah. So what those are
Mhm.
characterizing is potentially different branches of what we would call, say, the moduli space. This is assuming, of course, that we do have a moduli space at all. Assuming that there's kind of no quantum corrections and so on, then we could talk about kind of the classical moduli space. And if you have enough supersymmetry, it's kind of an exact statement. And then what's happening is that the different blowups tell you about different kind of chambers or properties away from the singularity. So what one often does is you don't directly attack, say, the singular space. What you instead do is say, well, I have this singularity. If I deform it in this or that way, it corresponds from the field theory point of view to switching on kind of operator expectation values or different parameters that are moving you in the moduli space to different kinds of motions away from kind of the singular behavior. And so you can get very different effective field theories depending on how you blow it up. And so so there's a kind of usually like a chamber-like structure to the to the moduli space dictated by the choice of blowups. Yeah.
Mhm. So previously you referred to the original gut model by Glasher and Georgi SU5 model, and then you also
Yeah.
referred to SO10 models that people work on. So can you get SU5 and SO10 models out of brain intersection models?
Depends on how broadly we're talking about brain intersection. Do you mean in the context of, say, F theory or?
Yes.
Yeah, then you can get both of those. I mean, the level of success in terms of like really getting like exactly the field content and exactly the matter content varies a bit. I must say it's been a little while since I looked at the exact state of the art, but I think
Mhm.
it's still true that SU5 kind of got the closest in terms of producing kind of interesting standard model vacua. But yeah, for sure, kind of the big qualitative things are all kind of fine in either way. So one of the things that SO10 has, for example, is that all of the matter content of the standard model, once you also include right-handed neutrinos, are all in a spinor representation of really spin 10 rather than SO10. And so the question is, how do you make a spinner in kind of the 2A or 2B world? And the point is that that's not so easy to do because everything is kind of dictated by these open strings and you can't really make your favorite representations. Um, well, like the spinner. If you go to say F theory or M theory, then it becomes a little bit easier. And the way it comes about is that secretly there's kind of an exceptional group or something floating around. And then if you deform that thing, then it allows you to produce, say, the spinner representation. So yeah, SO10, SU5 guts, flipped SU5 is another one that is can be built. E6 guts can also be built, so like trinification models. It's part of the issue with as you start increasing the size of the group is that you can often get the matter content you want for the standard model, but there's also kind of usually some additional kind of what we would call exotics. So things kind of not necessarily that have the charges that you want. You have to somehow get rid of these extra things if you want to match to kind of the particle physics model we know about, say the standard model. And so getting rid of those things is kind of becomes trickier as you start going to the bigger and bigger groups. Um,
So how
so
do you get rid of those things? Do you make them heavy?
Well, sometimes you can, and sometimes you can't. So the problem becomes, if they're coming in chiral states, if they're coming as chiral degrees of freedom, then it becomes a little bit more challenging to get rid of them. Just because kind of the easiest way to get rid of a set of particles is if they come in like what we call a vector-like pair. So in other words, you have the particle in some representation, and then you have another particle in a conjugate representation. Then it's very easy to add terms to the Lagrangian, which give it a mass, and then as a result, remove them from the low energy spectrum. For chiral degrees of freedom, it's a bit more challenging to get rid of them. Although one of the things that I was actually thinking about doing at some point, I haven't done it yet, is kind of revisiting some of these kind of earlier models, but using this technique known as symmetric mass generation to see if you could kind of strip off kind of exotics this way. It usually requires thing that comes in like for 4D models to come in like multiples of 16 because you can't have any other anomalies floating around. If you have an anomaly, then you can't really get, you expect some remnant of the anomaly to even persist down to lower energies. But uh, but I suspect that there's probably some, clever way of talking about symmetric mass generation in these settings to kind of remove seeming exotics. The issue then would of course be how would you do this and not contaminate the rest of the model with strong coupling? So it's not a completely easy task to do this, but it's something that so yeah. So if you have chiral degrees of freedom, it's typically harder to kind of remove them, but there are ways of coupling it in clever ways to other matter to get rid of it. Yeah.
I see. So one more thing that I wanted to talk about, and that has some relation to F theory, is to get six-dimensional superconformal field theories from F theory, right? So
Uh-huh.
can you tell us a bit about that procedure? That how do you get? So as far as I understand, you do use Calabi-Yau threefolds, right? But
Yeah.
what are the details of this procedure, and what is the role that is played by singularities, and what is the role that's played by anomalies in this procedure?
Yeah. Okay. So for 60 CFTs, okay. So the first thing is it's pretty surprising that you can talk about kind of higher dimensional conformal field theories at all. So kind of, I would say before the kind of 1990s, the only examples of CFTs were pretty limited, both in terms of, just Lagrangian examples, but also even like even like finding interesting 4D examples of conformal fixed points is pretty tricky. So there's kind of two things that are being leveraged here. One is having supersymmetry. So, of course, there was this great work done by Seiberg in the 90s and, many other folks showing that, actually you could start building lots and lots of examples of CFTs. And that was like a very dominant thing, just making 4D CFTs. And then uh, and also interesting, of course, 3D CFTs. But then also finding these kind of higher dimensional fixed points. And so so again, finding these like 5D and 6D examples of conformal field theories. And you could ask, how do you even know that these things exist? And the earliest constructions of these things came from, if you like, from looking at various kinds of singular geometries, and or basically starting with a brane configuration and then watching what would happen as certain degrees of freedom became very light as you entered the kind of what we would say the singular limit. So when you were getting close to making a CFT in the first place. So kind of the operating theme in many of these examples is, especially in 6 dimensions, you don't start necessarily with a CFT. You start instead with some other kind of low energy quantum field theory, but you identify some kind of massive string excitations. And then what you do is you start looking in the moduli space, and because you have supersymmetry, you can actually trust this thing quantum mechanically. You watch what happens as you start kind of tuning the vacuum moduli such that the effective tension of these strings is looking like it's going to become zero tension. Now, it's kind of a nonsense statement to say that you have like a local theory with tensionless strings. So you don't really have the tensionless strings right at the conformal fixed point, but it's at least providing you a way of seeing that, oh, something interesting is starting to happen right as we start taking this tuning limit. Now, what do these massless strings correspond to from the point of view of, say, type 2B, F theory, M theory, 2A, or whatever? They correspond usually to branes that are wrapped on internal cycles. And so they're wrapped on internal cycles, and then the volume of that cycle is shrinking down to become zero volume. Now, what does that have to do with this? Well, the brane comes with a tension, but then the effective string also has a tension, and it's dictated by the tension of the original kind of parent brane, but also the volume of the internal cycle. And so then as this thing shrinks down to zero size, the effective string tension looks like it's also going to zero. So now you could ask, what does this mean geometrically? Geometrically, it corresponds this kind of the reverse operation of the blowing up we were talking about. It's going to what we would call, say, a blow down, where you're kind of taking the curves or whatever and you're shrinking them down to zero size. Um, so what does that mean from the point of view of, say, F theory? What you're doing is you're looking for a specific class of geometries where you can start shrinking curves down. So in this case, you take D3 branes, you wrap them on complex curves, P1s, and you start shrinking them down. And then as a result of them shrinking down, you're building models that have these effective strings with zero tension. And then to kind of build a consistent model, you then have to say, okay, well, I'm in F theory, so I need to talk about, say, an elliptic fibered Calabi threefold, and it's one that has certain kinds of singularities, both in the base, where all the wrapped branes are coming to make the effective strings of the effective strings for the 6D CFT, but then also kind of the elliptic fiber over it. So you can get interesting things like gauge theories coupled to the effective strings, flavor symmetries coupled to the effective strings. So this is kind of the general machine for building basically all the known examples of 6D CFTs. Um, and as far as things like anomalies and so on, there's kind of two ways that those play a role. One is because this is a 6 dimensional chiral theory, you have to be very careful about whether the anomalies are canceled. So even if you're working off on the moduli space, you have a chiral system in 6 dimensions, and there's a version of the kind of celebrated Green-Schwarz mechanism down in 6 dimensions. So I think all the people associated with it in 6D are Green, Schwartz, Senyati, and West. I might be missing somebody, but they have there's a version of the Green-Schwarz mechanism down there, which is actually crucial for making chiral gauge theories, which are self-consistent. So kind of the degrees of freedom of the string are kind of actually necessary in order to even write down kind of anomaly-free gauge theories. So that's one way that anomalies enter, just in order to kind of have that piece. But then, of course, anomalies also play an interesting role in kind of constraining the dynamics. So a different kind of anomaly, not a gauge theory anomaly, but a global symmetry anomaly, then dictates what are the properties of this system. Can we start counting degrees of freedom in these systems? And one way to get at that kind of question is by computing all of the anomalies for these 60 CFTs. And by now, basically, there's kind of an algorithmic technique for given one of these 60 CFTs, how to read off the corresponding anomalies. So that's kind of the two ways that anomalies enter the story too. Yeah.
So you can start from one of these 60 superconformal field theories, and you can put them on a two-dimensional Riemann surface and make like a four-dimensional superconformal field theory. But can you
Yeah.
start from F theory and have, compactify it on a Calabi-Yau fourfold and make four-dimensional SCFTs? Will the procedure work there too, or is that different?
So we actually did look at that question, and so initially I was very optimistic it was going to work, but after we did the project, I became less optimistic that it was going to ever work. If you have, say, Calabi-Yau fourfolds. So the big difference between kind of Calabi-Yau threefolds and Calabi-Yau fourfolds is kind of the amount of supersymmetry being preserved. So the kind of setup you're getting for F theory on a Calabi-Yau fourfold will preserve 4D n equals 1 supersymmetry generically. So this is a situation that has kind of the minimal amount of supersymmetry. So it has four real supercharges if you kind of count it as kind of a Weil spinner in right? So that has 2 degrees of freedom, and each one is complex, so you get basically four real degrees of freedom. And with that low level of supersymmetry, some of the statements you make for 60 CFTs are just not as robust. So for example, saying things like, "Oh, I have an exactly BPS string," or something that's kind of protected with a string tension is protected in 6 dimensions, just doesn't work in 4 dimensions. That's one thing. The other thing is that even the structure of the moduli space can receive very strong kind of quantum corrections. So a lot of what you use when you have like a theory of 8 real supercharges, so n equals 2 in 4 dimensions or n equals 1 comma 0 in 6 dimensions, is that you have enough supersymmetry that the moduli space doesn't really receive quantum corrections, or at least parts of the moduli space don't receive quantum corrections. But with n equals 1, that's not really true anymore. So now why is that such a big deal for making a CFT? Well, what you're trying to do, at least geometrically, is you'd be taking cycles of various kinds and trying to collapse them down to zero size. But when you do that, you're kind of trying to extrapolate from kind of the large volume limit that you understand well to kind of these small volume regimes. And if there's no supersymmetry, then there's no guarantee that there will be any kind of protection against instantons or other kinds of quantum corrections that can start kicking in and obstructing the motion down to kind of the singular point where the CFT would be sitting. So in terms of pure geometry, the thing you would want is, in this case, kind of a collapsing Kähler surfaces that could be contracted or shrunk to zero size. And generically, you can have Euclidean D3 branes just wrapping those complex surfaces. And as a result, you just have a generic obstruction to making it work. Now, that's not, of course, the only way to make CFTs in 4 dimensions in F theory. If you don't have it be like pure geometry, so you have like the Calabi-Yau, but then you also bring in branes probing it. So, for example, D3 branes probing singularities, things like this. Then this is a kind of really kind of big machine for generating many interesting examples of SCFTs in 4 dimensions. But in terms of just doing it purely in terms of Calabi-Yau fourfolds, that's a much more challenging thing, and it typically fails for this reason. So we looked at this in particular in this paper. What is it called? Conformal Yukawas or something. It was Abruzzi, Morrison, and Tizano and myself, where we kind of said, let's play the same game we played in 6 dimensional CFTs. Can we do it again in 4 dimensions? And what we generically found is the dynamics are just different, and so it's not a C. It's still an interesting quantum field theory. It's just not. It's just not the one that would produce a CFT. So yeah.
So, does it also have to do with the fact that um, the singularities of Calabi-Yau fourfold are harder to understand as compared to Calabi-Yau threefolds?
Well, okay, I mean that's a technical issue, and so to some extent, yes, but like for example, in the models we looked at, we did do the blowups of the singularity, so it's not like
Mhm.
it's not possible to do those. I mean, the blowups are more challenging, obviously, because you're in higher complex dimension for the internal geometry, but it really is, I think, there's a physical limitation to, so it's not just like, oh, if I find my most clever geometry, I'll find you interesting examples of CFTs. It's more that there's a physical obstruction to doing this that you have to overcome. So it's not just a pure math problem anymore or a technical problem anymore. It's more that there's a generic reason it's not working. And understanding that reason is, of course, interesting. So uh, that's uh, that's I think where the project landed, where we could kind of see not so much the analog of making a CFT, but more something that Cyberg had observed in supersymmetric QCD with a low number of flavors. So when the number of flavors is equal to the number of colors, or number of flavors equal to number of colors plus one, you see a very different kind of characterization of what the moduli space looks like whether it will receive quantum corrections. So it's that kind of thing that we were instead seeing, not a conformal field theory, but instead this more interesting thing involving like more like either, chiral symmetry breaking or lack of chiral symmetry breaking or, confinement, things like that. That seemed to be more the structure that would kind of show up in that setting.
So what if we keep going and say that, okay, what about two-dimensional SCFTs like world sheet theories, like heterotic world sheet theory? Can you like use a Calabi-Yau fivefold and do that?
Yep. Yeah, so we did that too. So we
Okay.
did look at that. So in some papers I wrote with uh, Abruzzi, Hassler, and Melnikov, we asked exactly this question where you look at F theory on a Calabi-Yau fivefold and use it to kind of engineer interesting two-dimensional theories. And around basically the same time, there was another group doing basically the same kind of setup or game, both in F theory on Calabi-Yau fivefolds, but also heterotic on corresponding fourfolds by Schaefer-Nemeke and Wiegand, where they also looked at basically the same kind of setup. And there's a couple things that become tricky there in terms of, so you have to kind of be very careful about how you take what would be called so-called decoupling limits because you're in such low dimensions. So if you kind of start with these like non-compact geometries, or you kind of start right from that point, then you can start engineering interesting kind of 2D field theories, but also really 2D field theories kind of coupled to 2D gravity if it's like a compact Calabi-Yau fivefold. So the interesting thing that happens here is, so we were mentioning that one kind of singularity will give you the gauge groups. And then if you have a further collision of those, then you'll have, uh, the matter fields. And then if you have a further collision of those, then you'll get, say, a cubic coupling or some kind of interesting Yukawa. And then you could ask, oh, well, I'm down in such, low dimension. So there's actually a fourth thing that can happen. Four of these singularities can intersect each other. And you could ask, what is that thing? And it turns out to be some kind of other kind of interaction. And so the general kind of thing you build in this way is kind of candidate CFTs that came as the fixed points of gauge linear sigma models, but ones that have kind of 0, 2 supersymmetry. So they're kind of still holomorphic, but they only have kind of like a chiral supersymmetry to them. Um, yeah. So part of the reason why it gets more challenging as you go down in dimension is that this thing that you often want to do in these settings, which is to kind of freeze the vacuum moduli. So in other words, you want to imagine that you have like a modulus and you just switch on like a background expectation value for it. That works very
Mhm.
well in 3 dimensions and above, but in 2 dimensions and below, it doesn't work so well because the field can more easily wander. So for example, you can't really like freeze the value of this thing off at kind of infinity. Instead, it will start to wander more. And if it's wandering around and exploring things, then there's not really a clean sense in which, you kind of completely decoupled or thrown out certain features of the compactification. So this kind of scaling limit becomes more challenging as you go down to 2 dimensions. It's not impossible to do, so you can still study many properties of it, but it's just a general kind of feature that's happening that when you're down trying to engineer 2D models, then you have to be much more careful about what the moduli are doing and fluctuating. And
So
so actually, as a follow-up to that work on F3 on Calabi fourfolds, we actually went back and looked at a particular, if you like, baby example of this, which is like 60 CFTs on different kinds of four manifolds, to look at the kinds of two-dimensional systems you get in that setting. Uh, and you can actually kind of reverse the whole game by looking at, well, the moduli don't quite stay put, they're fluctuating around. And so because they fluctuate around, it means that kind of different branches of supposedly different classical branches of the theory will actually quantum mechanically blend into one another. So that's what we also did in another paper with Abruzzi, Hostler, and Melnikov,
I
looking at
see.
that too. Yeah.
So, a natural question that arises from here is that, so since Calabi manifolds come in even real dimensions, you can't get something like a 3D CFT from a Calabi manifold. So if you want to get a 3D SCFT from F theory, can you get that using some compactification or, for example, ABGM, something like that?
Yeah, I mean, like a very lazy way to do it is to start with a 4D model and then go down on a
Yeah,
circle and
sure.
and twist it in some way. And so that's kind of a generic feature of doing that thing. But I mean, often what you can do, and so by the way, that's not as like bad as it might sound, because there's also an M theory, F theory duality. And so when you
Mhm.
have F theory on a Calabi-Yau times a circle, then there's another kind of characterization of the thing in the limit where the circle is shrunk to small size. which is M theory on basically the exact same Calabi-Yau. And now, if you have M theory on a Calabi-Yau, then you start producing odd dimensional quantum field theories. So, for example, what's a nice way to build 5D CFTs? You can start with F theory on a 6D CFT, compactify on a circle, uh, on F theory on a Calabi-Yau threefold, compactify further on a circle, and now you're talking about M theory on basically the exact same Calabi-Yau threefold, up to kind of some scaling limits things happening. Okay, but that's a nice way to build 5D CFTs. And you can play the game again, like saying, well, I have my favorite 4D theory. I'll compactify again and get a 3D theory. And in fact,
Mhm.
many of the kind of most robust results we know about for 4D n equals 1 F theory vacua come from playing this game where you say, well, I'll go down on a circle and I'll tell you the kind of 3D theory that I get. And so I myself have not tried to like engineer like ABJM too carefully in this setting, but I think it can be done without too much hassle.
So for example, in 5 dimensions, you have these theories called EN theories. You can do that thing on by M theory on Calabi-Yau threefold, right?
Yeah.
I see. So one more question that I have is that so there is this conjecture that superconformal field theories don't live in dimensions more than six. Do you think that we can have some insight on that conjecture using this F theory route?
Well, I mean, for SCFTs, it's not really a conjecture. It's more just like you can't do it because the algebra doesn't work. Uh,
Yes, true.
so the interesting thing about SCFTs is that just if you try to write down the kind of something that will combine the kind of conformal algebra and the R symmetry algebra into like the so-called superconformal algebra, then you kind of run out of room once you get to 6 dimensions. Like there's nothing available to you beyond that point. And so, I mean, that was the statement from like Nahm back in Werner Nahm back in like the 70s or something. But of course, the open question was, can you actually build examples? So you kind of say it's allowed by the symmetries, but is it? So that's one side of the story. The other side of the story, though, is what if you didn't have, say, supersymmetry at all? Then there's no real constraint. You can write down the conformal algebra in any dimension you like.
Mhm.
Uh, it'll just be, SO d comma 2 for a d-dimensional spacetime. So, okay, what's wrong with that? And there is nothing wrong with it. I mean, you can so a natural question is, could you build or engineer a 7-dimensional conformal field theory or an 8-dimensional conformal field theory? Presumably these things well, you know that you can't write down a weakly coupled Lagrangian description. Like that's already kind of out for 5D and 6D CFTs, but
Mhm.
it's a natural question to ask, could you make a non-supersymmetric 7D or 8D CFT? And I actually suspect the answer is yes, that there are these things. It's just harder to kind of build them because you don't have supersymmetry, obviously. But I'm pretty sure that they exist, and I think actually that one of the objects we already wrote down, we were already kind of conjecturing this, but I think we have more evidence for it now, is that these branes we talked about in a totally different context and connected with the swampland cobordism conjecture that these so-called reflection 7 branes, I actually
Mhm.
believe now that they have that they are 8D CFTs, for example. And so I'm pretty sure that that's a correct statement actually. I mean, of course, characterizing the CFT, saying like, okay, great, it's a CFT. You attached a name to it. What can you tell me about it? That's I think the open part of the game. Like, what can you actually compute about the thing? But in terms of it being a CFT, I think all of the kind of evidence that we already have, it seems to be its strong coupling, it's non-supersymmetric. It doesn't look like it's produced by anything involving just weakly coupled fields, and it doesn't look like it's gapped or anything. So what else could it be other than kind of an interacting fixed point? Uh, so
Right.
uh, I mean that's the kind of the qualitative thing that's already out there, and we were already conjecturing that. But I think we're starting to get better evidence that it does make sense as a non-supersymmetric CFT. I mean, obviously, I haven't written a paper saying this is a CFT for sure, but I'm pretty sure that it's a correct statement. Yeah.
Okay, that's interesting. So
Yeah.
I was actually going to talk about reflection seven brains, after this topic. So since you have mentioned that, let's talk about that. But before
Okay.
talking about reflection seven brains, I want to ask you this question. So in your PhD, you worked on F theory and gut model building and things like that. But
Yeah.
now you work a lot on generalized symmetry. So what made you interested in generalized symmetries in the first place?
Well, it was kind of an interesting route for me. I mean, so the trajectory of things I worked on was I did a lot of, I would say like particle physics slash string phenomenology type stuff for my PhD work. That was kind of the F theory stuff. And then one of the things that happened during that work is I started becoming interested in kind of kind of what comes after the standard model. So kind of extra sectors that you could kind of easily add in or that are kind of natural to expect to occur. And a big class of these things were kind of strongly coupled quantum field theories that you kind of just have as an extra sector, an interesting extra sector coupling into the standard model. And so uh, that kind of meant or that led me to think more about, just strongly coupled CFTs in their own right. First in four dimensions as coming from these F theory models, but then later on in terms of like how they would interact or how where you would get these things from. And that led me to think more about 60 CFTs. And then basically, I would say a year after the generalized symmetries paper, maybe even less, we we started okay, so one of the things, well, one of the initial lessons, I mean, obviously one of them is that symmetry operators are topological, but one of the other kind of lessons, I mean, I think this was already known to all the experts, but it wasn't known, or I hadn't appreciated it, was that if you want to tell me what kind of quantum field theory you're talking about, it's not enough to kind of specify just the local operator content. You have to talk more about the spectrum of extended operators you get to speak about. And I was very intrigued by this statement because then the question came up, well, I know some things about 60 CFTs. Have I done a good job characterizing them? Or are there, other things I should be telling you about, like the spectrum of extended objects, defects, those kinds of properties? And so it turns out that all those defects get acted on in interesting ways by generalized symmetries. And so it became a very natural thing to just ask from the point of view of engineering and interesting quantum field theory and string theory, what are the kind of symmetries of the system, and both to constrain it and just to study them in their own right. In particular, I mean, there's of course been a ton of work on generalized symmetries, uh, but there wasn't so much at that time, and still, to some extent, not as much on, just asking for these more intrinsically strongly coupled systems where it's harder to write down a Lagrangian, harder to kind of study it using some other method. What are the symmetries of those systems? So I thought this would be a very natural thing to kind of explore from initially from just that point of view. And so that kind of
Hmm.
led me into thinking more about kind of generalized symmetries. And
I
so,
see.
so this kind of the first thing was like this thing in 2015, I think, around then. It was like a year or two after the big generalized symmetries paper,
Mm,
where we introduced this notion of what we called like a defect group for that thing, um, and then it was later appreciated that actually this defect group thing is the thing that computes for stringy engineered quantum field theories, things like generalized symmetry, so things that act like as p-form symmetries in that. And so once that came out, then I realized, oh, well, this is something I know about, and it's something that I think I could meaningfully contribute to. And so that's why I started thinking more about that, both, as a topic in its own right, but also kind of to address questions I had about earlier stuff I'd been working on. Yeah.
I see. So I want to understand a statement that you made a bit better. So you said that a QFT is not specified by just its local operators. You have to specify the extended operators as well, or aren't the extended operators like determined by the QFT itself?
Well, okay. So for example, let's say we just do, I'm just saying like in the context of like textbook QFT,
Hmm.
and I say I'll give you say Yang-Mills theory, for
Yes.
example, right? But all I tell you is the kind of the Lie algebra of the theory, right?
Right.
So then the question is, all right, did you want to tell me about SUN gauge theory, or did you want as a group, or did you want to tell me about SUN mod ZK? Where k divides n. Uh,
Right. Right. Right.
so what would that dictate? That would tell me about what kind of Wilson lines I'm allowed to entertain in the. So these are more like extended operators, and it's often not even fair to just say I'm going to characterize everything totally locally. So take for example, I don't know, Chern-Simons theory. There's not
Yes.
many local particle excitations you could talk about, but you can perfectly well talk about kind of the Wilson lines. I
Hmm.
mean, there's ways of thinking about, Chern-Simons theories kind of being built up from kind of these like coupled wires constructions where you have, you know,
Yes.
2D CFTs, you couple left and right movers in interesting ways to build up kind of the gapped bulk. And so in that sense, you say, oh yes, there is local degrees of freedom, but that Hilbert space is totally different from kind of the quote unquote Hilbert space of the bulk. So for those reasons, I'm saying that it's usually not enough to just say statements about the kind of operators supported on points. Typically, you have to say more about kind of the extended operators in their own right. and also the
Right.
defects and boundary conditions. That's all I meant by that statement. Yeah.
I see. So if I talk about a very special quantum field theories, which are CFTs, so the common law is that if you specify the local operators and you specify the OPE coefficients, then
Yeah.
you have specified the CFT. So is that statement correct?
At some level of approximation, yes. But you could ask how many different theory. I mean, what's the kind of form of the global symmetries in that system? Do you have any choices about that? So those kinds of subtle things are not going to show up necessarily in like a local OPE coefficient. So
Hmm. True.
so it's yeah, this is more like tell me things about the partition function of the CFT. Do you think you understand it completely? And so the partition function you expect for like say SUN versus SUN mod ZK is not going to behave the same. And the question is why? And I would say it's due to kind of not necessarily like local operator data.
I
So,
see.
but I mean, obviously, if you knew all the OPE coefficients, you would declare victory and say that you knew the CFT. I mean, that's obvious. This is more just more nitpicking at that point, I would say.
I
Yeah.
see. So before we talk about the reflection brains, I want for the audience, can you describe a bit about what is the Swampland program and specifically what is the cobordism conjecture and the no global symmetries conjecture?
Yeah. So the Swampland program in general. Uh, So I may not be the best person to characterize it, or maybe I am because I don't always work on it. So from my point of view, what is the Swampland program aiming to do? The idea is to kind of, I would say, come up with, if you like, the principles of quantum gravity from kind of a bottom-up point of view. So if you wish to remain agnostic about like is string theory correct or something like that, and you want to know what are kind of the driving principles of quantum gravity, the idea is to come up with kind of principles that would allow you to kind of reconstruct and see that, ah, yes, I had no choice but to arrive at string theory in the end. Because one of the things that's kind of missing is like, what is the analog of, say, the equivalence principle that you have in general relativity? What is the analog of that kind of statement in for quantum gravity? And so there's all these interesting conjectures, and of course they're motivated by string theory examples because that's basically the only example we have of a quantum gravity that doesn't kind of fall apart right away. Uh, it's motivated by those things like, well, this is what we know about in all these examples. Can we kind of demonstrate that it's true with not necessarily putting in the inputs of string theory from the start? So it's kind of a mix between kind of top-down reasoning, but also kind of marrying that with like a bottom-up way of approaching this. So saying, did I understand the core principles that were necessary in order to kind of characterize what I meant by quantum gravity in the first place? So, there's one attitude which is that, oh, you can make any effective field theory you like and stick it inside a string theory. That is for sure not correct for many reasons. But then the question becomes, well, what kinds of quantum field theories can you make? What kind of effective field theories? Is there some general principle, some general lore about the kinds of things you can make? What kind of backgrounds are admissible? Can you have, I mean, so one of the more controversial ones would be, say, is there anything such thing as like pure de Sitter space? Are there scale separated ADS vacua? So these are kind of the more controversial ones. But the point is again to say, well, is there some kind of basic principle about why? And so a lot of the style of argument in the swampland community involves picking really clever examples and showing that, well, this is the general principle, and we can see that it works in all the examples we can think of. So perhaps it is true just in general. The criticism, of course, is that people say, well, we just don't understand string theory or M theory or F theory well enough. So how do you know that there's not some other corner that you might have forgot about? So
That's why
that I
they're
would
called
characterize it as
conjectures, right?
what's that?
That's why they're called conjectures, not like
Yeah, that's why they're
principles.
called conjectures. But many of the conjectures range from, I would say actually very solid, and there's a ton of
Hmm.
evidence for it, to kind of more controversial ones. And, I mean, I talked to them, a lot of them. I mean, my PhD advisor, Kamran, is, the main guy on it. And, in many cases, they say, well, okay, if you really think you have like, a great example of de Sitter space, what is it? Just show me, you can kind of back, throw it back and ask that kind of question. So yeah, I mean, many of the conjectures are provocative for that reason, but many of them I think also kind of stimulated a lot of like investigations that probably wouldn't have occurred if these conjectures hadn't been put forward. Um,
Hmm.
so in terms of the swampland cobordism conjecture, uh, I started becoming interested in it actually from the point of view of kind of generalized symmetries, and there's a way of viewing it from that. So what is the cobordism conjecture telling you? It's telling you, so in formal terms, it's saying that you can every space-time is allowed to kind of terminate or end in quantum gravity. But there's a way of thinking about what that is in terms of a generalization or a gravity version of the statement that there's no global symmetries expected. So generalized symmetries can kind of be characterized as a more broad notion of what it means to have a global symmetry. And if you have cobordisms, so what is a cobordism? It's a kind of equivalence relation between certain kinds of manifolds. And you often equip it with additional structure. So it might have extra bundles, or you might say, I demand that spinors make sense, or maybe it has a pin plus structure, some other kind of structure that you attach onto the manifold. And you say, what are the equivalence relations between these? And the equivalence relation is you look for some one higher dimensional bulk manifold which has as its boundaries the two manifolds that you want to say are equivalent to one another. So often people write these kind of interpolating geometries where on the left you have one manifold and it kind of does some kind of tube or cylindrical like thing to another one. But strictly speaking, that's not necessary. You could just say that I have a bulk manifold and it happens to have two boundaries, and that's how I set the equivalence between these two things. So what does cobordisms have to do with any of this? The point is that if you have a non-trivial cobordism, so cobordism class, so in other words, one that cannot be completely, gotten rid of. So in other words, it doesn't kind of just terminate on nothing. Then it turns out that this builds you an interesting defect in your effective field theory or your effective theory at low energies. And there's a corresponding generalized symmetry acting upon that defect. So in other words, the cobordism group itself becomes basically the group of charges, or tells you about charges of or non-trivial global charges in the system. But if you believe that there's no global symmetries in quantum gravity, then you're kind of in a bind. So how do you get rid of it? Well, you say, well, actually, there was a state I forgot about that allowed me to kind of get rid of the generalized symmetry in the first place. So as a classic example, right, in like Maxwell theory, you have interesting, line operators that you can talk about, and they get acted on by a one-form symmetry. So it just acts on it and rotates it by some phase. But if you start adding dynamical electrons in, then those lines can terminate. And then the symmetry is essentially kind of gone. The candidate one-form symmetry you had is completely gone. Or if the electron has charge, I don't know, Q, then it gets broken to say Z mod Q, or you're left with just Z mod Q. And there's a very nice way of thinking about that, the analog of that electron as kind of the extra thing you're going to add in as predicted by the Swampland cobordism conjecture. So basically, the analog of sign of the defect is this cobordism defect. The line operator is the cobordism defect, and then the thing that kind of terminates the analog of the electron is instead this kind of extra dynamical thing that you've added into the spectrum. And so what's exciting about this is, first of all, actually a very incredibly sharp mathematical statement. Like even though nobody knows what the cobordism group with quantum gravity would mean, cobordism groups have been studied by mathematicians for a very long time, and it's a very, well-developed, mathematical setup. So you can go out and you can start calculating these things, and you can ask, okay, if I think that the cobordism conjecture is correct, I should be predicting certain kinds of new kinds of states. Maybe I've seen them already, maybe I haven't. And so one of the remarkable things is that you do this and you kind of post-dict many of the things you already knew about, like D-branes, orientifold planes, and other things. But at the same time, if you kind of now say, okay, that's good evidence that it's working, you can now kind of flip it around and ask, well, what are the kind of other objects that might be out there that I don't necessarily have control over from, say, supersymmetry or string worldsheet? What are the other things I can talk about that might be out there? And so the reflection seven brane is of that kind. It's this kind of new thing. You compute a certain kind of Bordism group, and as a result of that, you find that, well, there's this new thing hanging out. Um,
I see.
yeah.
So first of all, why are they called reflection branes?
They're called reflection branes because of like the F theory terminology. Um, so in F theory, right, what we do is we start, so we're accustomed to thinking about 10-dimensional spacetimes in string theory. And in F theory, what we do is we kind of decorate that 10-dimensional spacetime by some auxiliary 12-dimensional geometry, which is characterizing the profile of this like axiodilaton for 2B. And so what's happening is there's a seven brane, so it's filling eight out of the 10 dimensions. So it's codimension, real codimension two in the base. And so it comes with kind of a branch cut that kind of sticks out. So if you look at the kind of two directions transverse to the brane, there's some line that sticks out. And then if you kind of wind around it, what's happening at the level of the F theory torus is that it looks like there's a reflection on either. So if you view the F theory torus as kind of a square with the sides identified, then what's happening is that one of those sides is being reflected. Uh, and so that's why we called it a reflection seven brane, because it's doing this reflection either, kind of in the up and down like cycle like this, or the left right cycle like this. And so
Hmm.
those things have nice 2B interpretations too, by the way, in terms of either world sheet orientation reversal or in terms of left moving fermion parity.
So can you have reflection branes of other dimensions, or do they have to be seven-dimensional?
Oh no, they can have you can have other ones. So in a recent paper we wrote with my student Vivek Chakrabarty, Arun Dabrai, and Marcus Dirigel, we looked at exactly this question in the context of say M theory,
Hmm.
where we said more generally, okay, what if we just have some bigger torus or something like that, and we play the same game where we reflect and so on. And indeed, we found examples of reflection branes in all those different situations. Uh, part of the trick is to understand better whether you're allowed to do these reflections in the first place. So the kind of underlying part of the story is, in the context of say 2B, it's customary to say that the duality group is like SL2Z or something like this.
Hmm.
But actually, what was appreciated later by I believe the first people or the people I know about who did it were Pantev and Sharp, and then there was a paper by Tachikawa and Yunakura, and probably forgetting somebody on this. Anyway, so what they did is they found that there's kind of there's lifts of these general structures to include so-called like reflections on the torus, and that's for a T2. And then you could say, what about for a T3? What about for a T4? Do I still get to talk about these reflections and these pin plus lifts of these structures? And so part of what we were doing is first figuring that out, and then using that to then compute the appropriate cobordism groups, and then using that to then predict that actually there is a non-trivial defect you can't get rid of for these other setups. So reflection branes make sense, I think, in many dimensions. Uh,
So correct me if I'm wrong. So in your paper, with a number of authors, one of them was Miguel Montero and then Arun Debre. It was called Chronicles of Two Bordia. So
right.
in that paper, you talk about our seventh brain, and that was non-supersymmetric. So all of these reflection branes have to be non-supersymmetric, or can they be supersymmetric?
They're all non-supersymmetric as far as we understand, and it's basically just because you write down kind of you look at the kind of candidate spinners that you would have, and the spinners are kind of getting sent to their complex conjugate. So it's a very kind of non-holomorphic thing. So the general reason you should expect it to not be supersymmetric is that holomorphy is completely screwed up by the presence of this brane. So for example, if you look at the shape modulus controlling the elliptic curve, it's controlled
Hmm.
by a complex parameter tau. And then as you wind around this thing, tau, this complex parameter, is sent to minus tau bar. So in other words, minus the complex conjugate of tau. And this kind of non-holomorphic behavior is usually a good signal that something got messed up with supersymmetry. So usually in supersymmetric backgrounds, again, like one of the kind of big insights that Seiberg had early on about supersymmetry is how strong holomorphy is as a constraint on many systems that have supersymmetry. And basically, it's the same thing here. You screwed up holomorphy right from the start, and you can see it kind of messing things up. Yeah.
So it breaks all supersymmetry, or does it break partial supersymmetry?
No, it breaks it all. So the typical thing for like a brain solution, right, is that you break half of the supersymmetry or something like this.
Hmm.
This is doing something much more violent. So it's really because it's completely hol there's not even like a part of it that gets preserved. Yeah.
I see. Okay, so there is one more thing that I want to talk about. So there is this paper of yours called Falsifying String Theory at the Collider, right?
Uh-huh.
And in that paper, you mentioned this fact that if you talk about, sorry, if you talk about, scenarios that can be built from string theory, you always get particles that live in lower dimensional representations, right? So if you have, a single majorana particle that lives in like five or higher dimensional representation of SUL, then that's like falsifying string theory. Uh, so my first question is that do we have, I think, and you do talk about this in your paper, do we have a no-go theorem that you can't have, sorry, that you can't have particles which have like higher dimensional representations that come from string theory, or that's just a conjecture?
Okay. So so there's a key piece of the statement that it's not just that you don't have the high dimensional representation, but it's the high dimensional representation in isolation. So,
Yeah.
for example, a very kind of well-known way to build pretty high dimensional representations in string theory is through, from the heterotic point of view, is through called so-called higher Kac-Moody levels.
Yes.
So this is a general way to kind of build, for example, guys into five-dimensional representation and so on. Now, the thing that you have when you do this, however, is not just the thing in the five-dimensional representation. You get the five, but then you also get things typically in the four, the three, and the two. So you never get
Yes.
it by itself. And so part of the issue, and by the way, you can also kind of engineer loads of quantum field theories that do roughly the same thing. So for example, you can talk about, say, the pions of QCD. Those look like they're in, in adjoint representation. And then you also have, baryons and all the other hadronic resonances, whatever you want to talk about. But
Right.
you never get the thing in the high dimensional representation of the flavor symmetry by itself. There's always a whole tower of things that come with it. And
Right.
so just by kind of sorting through all the examples we know about, both from the field theory point of view and also from and field theories that we know can embed inside of string theory, and also just looking at all the known examples in the landscape of vacua. So people talk about how big and vast the landscape is and so on. I think it's fair to say that not one of those examples has this kind of scenario where you have just the five-dimensional representation and nothing else. Now, at the level of
Hmm.
like a sharp no-go theorem, I'm pretty sure we're going to be able to prove, pieces of this in various regimes. So, for example, for weakly coupled heterotic models, or for certain kinds of strongly coupled QFTs, I'm pretty sure we're going to be able to show that there is no such thing as like a five in isolation. It's again, it's very crucial that it's just in isolation
Hmm.
because there's plenty of ways to build crazy composite bound states, but you don't just get the composite bound state. It's usually accompanied by a ton of other stuff. That's kind of
Yeah.
the key point. That it's not there's nothing else in there. And so, yes, it is a conjecture. Part of the reason why we picked the title we did is because I'm pretty sure it's a true statement. And also, I think it is definitely a true statement that the entire landscape of known vacua, uh, I have never seen a model like this. And I can say actually my own kind of trajectory towards thinking about this, which is that when I was in graduate school and I was thinking about, building interesting particle physics models, I learned of this, very exciting paper by Strumia, Cirelli, and I'm probably forgetting somebody else. Yeah, where they talk about a scenario called minimal dark matter. And basically, they wanted to explain a bunch of, interesting dark matter experiments that had come out. And all they said was, well, just add this one particle and we will explain everything for you. And it has to have a certain mass, et cetera, et cetera. But I found this to be a very amazing statement that, this one particle could do all this stuff. So I thought, that's great. Let's go build it. And I tried for many times to, build this thing. And, you could kind of get it with these higher Kac-Moody levels, although embedding that in the standard model is also like a complete mess. So it's even if you wanted to go the route of higher Kac-Moody levels, like getting it like coupled to exactly the standard model is going to be just, I'm pretty sure it won't work even then. But putting that aside, I couldn't find any model that would do this job, and maybe there's some clever way, nobody has thought of yet, but I spend a lot of time thinking about it, and I'm pretty sure, there's qualitative reasons to expect it's not going to work. So, for example, that open strings come with two ends, things like this, right?
Hmm.
And the minute you want to build higher representations, what do you do, at least in string theory? You start talking about bound states of those objects. And once you start talking about bound states of objects, well, usually you don't get a bound state by itself. It usually is accompanied by many other states. It's not just in isolation as this single thing. So what we're looking at right now is indeed just how strong a statement can we make? Are there kind of more general no-go theorems we can put forward?
Right.
Yeah, so at that level, yes, it is a conjecture, but I think it's an incredibly well-motivated conjecture. Yeah.
I see. So in your paper, you do talk about the signatures that one must see to falsify string theory. But someone may ask this question that what should one see at the collider to know that okay, the thing that you said is happening? What is the experiment that one can do to find out if it's falsified or not?
Well, I mean, so we list actually. So what we did is we basically repurposed the so-called Chargino searches for this five
Mhm.
plit scenario. And the point is that this has a pretty distinctive signature in terms of a certain like disappearing track in the collider. And so it makes it through basically a piece of the collider, and then it basically just decays out to kind of the neutral bottom state. So the bottom state is electrically neutral in the 5-plit scenario. And then the point is that that has a very specific signature in the collider itself. And so that's something people are already looking for in the context of searching for charginos. The only thing that changes at that level is uh, that instead of having, say, the chargino, which is going to be like, say, in a coming embedding in, say, a 3-plit or something like that, it's instead up inside this big 5-plit. Now, in terms of the limit you can set with, like, LHC or something like that, it's not that great. So kind of minimal dark matter, it's still a totally viable scenario as far as I understand. But the scales you're talking about there, like where you would really want to, say, oh, this is actually motivated also by dark matter, is, more towards the kind of 5 to 10 TeV range. I think it might even be like a 13 TeV or something. So the point is that that's a much higher energy scale than you can kind of access directly through something like LHC. And so, the limit we could kind of set with available data is, it's good, but it's not kind of cutting into the kind of the most interesting part of the kind of parameter space. So I mean, obviously having another collider that's bigger would help with that. But if somebody comes along tomorrow and says, "Look, we have great evidence now for minimal dark matter," and one of my colleagues on the paper, or one collaborator on the paper, Matt Baumgart, is on some of these experiments. Uh, that would, if they saw it, that would be really striking. And I would at that point probably say that the version of the landscape that we know about probably is not correct. If you had that kind of like very sharp kind of thing coming out from either indirect detection or from colliders. So I view
So
this more like a proof of principle type thing, like seeing like how far can we push it in constrained string theory. Yeah.
I see. So since you are mentioning, the dark matter scenario, uh, do you have any like strong opinion about the dark dimension scenario?
Uh, I mean, it's an interesting idea. I mean, I don't know how. I think it's motivated by a lot of the swampland type stuff, but at the same time, like the thing that I would be more excited about on that is if you could actually come up with a explicit string theory realization. So it certainly is motivated by many of the string theory swampland or the swampland type style conjecture things. And it seems okay as like a phenomenological scenario. I don't see any problem with that. But what I would hope for is that, finding some way of embedding it inside of, even a prototypical string theory example, maybe just like here's the qualitative way it works and so on. So I wrote one paper with Kamran Fangjan and Timo where we were looking at, can this kind of structure be made compatible with other things you might be interested in, like say grand unified theories and so on. And so initially I thought it wasn't going to work at all. And the reason is that, you kind of dropping the size of the extra dimension so low that I would have thought that like proton decay would immediately kind of kill the scenario. And so I kind of view that work that I did there as kind of showing that these are the kinds of things, or these are the kind of hoops you would have to jump through in order to kind of have both grand unification and the dark dimension simultaneously. And so on its own, it seems like a interesting scenario. But again, I would be, and I have thought about like how to kind of try to UV complete it embedded in string theory. Not too successfully, I should say, but I think that would kind of make it more interesting for me. But as a phenomenological scenario, sure, why not? I mean, sounds good.
Okay. Okay, so I have a couple more questions before I go to some people's questions and then we can wrap this up. So, um, most of your papers are in collaborations, and even in your PhD, you wrote a lot of papers in collaboration. So my question is that do you have any advice on building collaborations in PhD?
Uh, the main thing is just listen to your advisor. Uh, So it's not actually I would say that's actually much more important than like saying I must work on this exact topic. It's much more so kind of the role of I kind of view the advisor or something like this is not just giving you a sense of what is important now, but also kind of building the skills for what might be important in a few years from now. So I mean, what's the hot topic of the day kind of rotates around and it won't be hot forever or whatever. But kind of having a kind of a broad base of things you kind of understand and know about can help. And finding collaborators you can talk to again, like and people who will kind of help you learn is I think the most important thing. And I mean, in terms of at least for myself, and in terms of collaborating with folks, I would say, being generous and not like, I don't know, secretive or, greedy is probably like a very helpful thing to do. So, I mean, I don't know, maybe I should have been more, tight-lipped on certain things, but I would I talk to people about, whatever I'm interested in. And, I find that I'll learn more from talking to them if I kind of open up and tell them what I'm interested in, what I'm thinking about, rather than, keeping everything a secret and like not keeping it all in. And I mean, the other thing though is just in terms of like building a collaboration is kind of having the freedom to, I don't know, say stupid things. So being able to, say, I think I'm not sure if this is what I think is going on, because everybody will say, incorrect things from time to time, but, they will also say things that, you might not have thought of, and you want to, I would say, encourage that kind of openness. So, I mean, other people have different attitudes. I mean, I've also been, part of collaboration, some of which haven't been so successful, where it's, much more stifling and, people are just like, nobody wants to say the wrong thing and it becomes very difficult. And I don't know, at least for me, I find it more, stimulating and productive to kind of being open and saying, like, well, what about this? What about that? And so I find that like helps in terms of building collaborations. Or I know
I
this
see.
person, he knows about this. Why don't we talk to him about this? Rather than saying, oh, we should figure it all out ourselves. Yeah.
I mean, so I'm sure you have more experience talking to students than me. Don't you think that junior students are more, scared to say the wrong thing because they think that it will give a bad impression of them to senior people? Or do you think that that's not the case? Everyone does it.
Oh, for sure it's the case. But I would say also, once they see me saying kind of, you know, incorrect things or not worrying about it, I think it helps. So for example, there's these. I mean, I remember giving like a seminar, I think at the UT Austin where like Weinberg was, and the kinds of questions he would ask, it was like this is like like a beginner's question, like why is he asking this? But the point was like he didn't really care. He just wanted to say, well, I'm interested in knowing what's the, so he was more interested in learning for himself. And so I think if you have this attitude of, being open and saying, I'm willing to, look like a fool if you like to learn more, then I think that's actually much more productive than being scared about what other people are going to say about you and worry about, oh, do I look foolish from asking this question? So at some level, you should just, I don't think, care. I mean, so yeah, I mean, hopefully my students feel free to ask questions, but
I'm pretty sure that if I say that to a student, the student will say that, well, if you are Weinberg, you can say that.
yeah, but how did Weinberg get to be Weinberg? By
Sure.
by asking questions like this. So
I
yeah.
see. So one more question that I have is that do you have any advice on how to choose a problem to work on? Because some people say that you should mostly work on what's hot in the field. Some people say that you should only work on the things that excite you. And there are some other criteria that some other people have. So do you have any advice on how to choose problems to work on?
I would say, well, at least from my own experience, usually it works out best if it's number one, something I think I have kind of, if you like, a comparative advantage on relative to other people. So maybe like I know more about this particular area, so I have an unfair advantage on something, or I happen to have worked on it. That's one thing. But on the other hand, it has to be something that, A, it's something I'm reasonably good at or I know about, but B, that I'm interested in. And hopefully there's some intersection between the two. So it could be that, I'm good at something and I don't want to work on it anymore or something like that. Well, you have to be willing to put in a large amount of time in order to get anywhere with it. So uh, it has to be something you're willing to spend time with, in chewing over and thinking about. And you may not get the answer right away. So there's many times in like many research projects I've had where I've just, you completely hit a brick wall or you don't know what you're doing. And it's only because you're interested in continuing in that direction that it will kind of
Hmm.
bear fruit eventually. And so, I mean, that's the other thing I would say would just be patient and if you like stubborn. I think those are more important than like picking the exact hot topic at the moment because I mean, of course it's important. It is important to like pick something that's, topical, like especially for getting hired in certain areas. But at the same time, I mean, honestly, the job situation is not great, period. And so you might as well do something that is interesting to you than
Sure.
just trying to, follow like the latest trend. So I mean, another way of putting it is I think this is actually much more important, is that you have to be kind of known for it's much more important to be kind of known for doing something rather than just like being observed as kind of following whatever the latest trend is. So it's like, oh yeah, that guy did this, then that's a much better situation to be in than to be in a situation where like, oh yeah, he wrote like all these interesting papers and there was a bunch of people working on it, and so everybody has a lot of citations in this giant mob of people. Then what's the difference between you and like the other N minus one people working in this area? Then,
Right.
so, uh, but if you can kind of say, I have this distinctive perspective and I am doing this very clear thing and I am clearly the one in control of the whole thing, then that is actually often much more appealing, for
Hmm.
also for like job searches and things like that. So, uh,
So correct me if I'm wrong, but can I say that you're saying that you should be known for something, even if that thing is not the hottest thing?
yeah, I mean, in some cases, it may not be the hottest thing right now, but it becomes hot as a result of what you've been working on.
Hmm.
Um, so I mean, I don't know. I mean, like you have these examples of people, right? And for many years, they're just ignored for, whatever reason. They're not working on the thing that's considered like amazing at that exact moment. Like, for example, take Weinberg again, right? The model of leptons paper was not like a big success right out of the gate. I mean, it had like a handful of citations for a few years, for many years, right? And then all of a sudden, all the stuff with neutral currents and started happening. And so or for example, Ken Wilson, right? I mean, that's another kind of classic example of a guy. I don't even think he had maybe he had one or two published papers when he got tenure or something. And, it worked out pretty well for him. And it was because, people were thinking, oh, this guy is thinking deeply about things. So, I mean, that's, I think that's much more important in the long run. I mean, in the short run, of course, like, like the problem is, of course, like the amount of time you have to work on these things is, kind of dictated by the kind of postdoc and faculty job application cycles, which are much shorter term. So you have to kind of be able to get your foot in the door. But there has to be, I think, like a broader long-term perspective. Otherwise, yeah, there's no point to it. So yeah, I mean, obviously, working on the hottest thing is good for it can be good for jobs and grants, but it can also kind of cut against you because what distinguishes you from, the other 500 folks doing the same thing?
Hmm.
Yeah.
Okay. So one more question that I have is that do you have any advice on how to handle multiple projects and multiple collaborations at the same time?
Have good collaborators. But
Sure.
I would say also, and this happens often in some of my projects, I'll sometimes be thinking about kind of related ideas, and I actually find that they kind of feed back on each other. And also, if I get stuck on one of them, maybe I'll take a little break from that one and start thinking more about the other one. So. Sometimes actually, the best stuff happens like after you've like thought for a long time about it, and then you pull back and take a break from it, and then kind of either work on something else, and then you realize randomly that the original thing you were working on.
Right.
So I would say like, being able to like take a breaks and also kind of organizing projects, like even if you're working on a lot of projects, organizing them like I would say semi-thematically. So like maybe you're working on different aspects of the same problem, but in many cases that can be helpful because then you can learn something about each one. Uh, so even though you're kind of moving on separate projects, they're all kind of in the same vicinity or moving in the same direction. That can also
Hmm.
be very helpful. Yeah.
So I'm asking this question because I've asked this question to several people and they have different approaches. So one thing that works good for me, and some people said the same thing, is that on a given day they work on a given project. They don't work on two projects on the same day because
Yeah.
it doesn't work for them. So do you work the same way or do you work differently? Do you work on several projects on the same day?
I don't know. It depends on my schedule, honestly. I mean, and sometimes I'll sometimes what I'll do is I'll start my day by just listing all the projects that I have and just thinking about what do I find exciting today. Uh,
Okay.
so
So,
uh,
so it's not that you say that, okay, on this day I'm gonna work on this project. It's not like that.
no, not for me at least. I mean, I'm pretty bad at kind of like having like some people really like meeting like on particular times and so on, but I find it much more productive to just randomly talk to people. So either on, like chat or just in person, I'll just walk by and say like, so what's going on? And I find that much more productive actually. Just kind of like being like randomly bombarded by things rather than kind of trying to plan it all out like either like on a regimented schedule and so on. Uh,
I see.
but
So,
yeah, I
yeah.
don't know.
So
Maybe I should do what you're doing.
no, no. I mean, I'm asking this question because different people have different ways to work this out. So, I mean,
Yeah.
what works for one person is not necessarily going to work for the other person. So, one more question that I have is that do you have any criteria before you select a PhD student? So, what features do you look for before you take a PhD student?
Uh, well, I mean, usually like so a lot of my work is on the more mathematical end. So or involves a lot of math, and so I typically look for somebody that has a good math background. That's actually I'd say so sometimes even like being like either like a math major or something like that can be very helpful to know. And so I mean the other thing that's very important, of course, for everything that one or at least what I do in high energy theory revolves in some way around knowing some quantum field theory. So if they've taken, for example, or they have some exposure to quantum field theory either on their own or they've happen to take it in, college or something like that, that that's also very helpful. It's harder to gauge like I mean, like nowadays for graduate admissions, like many people come with like, fully worked like projects like in papers, not just like on the experimental side, but also like even on the theoretical side. And so um that's that's a little bit harder to kind of gauge because, folks are at different kind of, stages of development and somebody who happens to like get their name on a paper, like how do you know that what they did? And so
Hmm.
what's become more common nowadays is to actually do, kind of brief interviews, like especially for folks who have like
Yes,
like a research project to just say like, okay, can you explain what you did in this paper and so on, just to get a sense of how much they knew or like this guy told me to do this and that's what I did. Um, but yeah, I mean, also kind of the other thing I personally look for is like, it's harder to kind of quantify or something, but some evidence that, you're not going to give up too easily. So I think that's actually, there's a certain threshold you must cross in order to be able to do the work at all. But then once you cross that, right, you can be the most brilliant person in the room, but if you kind of give up like the minute like something doesn't go your way, then that's not very good either. So that's typically what I at least look for when I'm uh, looking at like graduate admissions, for example. But
I
yeah.
see. So, one last question before we go to people's questions is that how to deal with failure in research or a setback?
Uh, well, t take a break or think about or try to understand why it went wrong. I mean, but often what I found is that things that I initially thought weren't going to pan out or something like that, I'll uh I'll try to summarize why it didn't work or write up a brief like explanation to myself about why it didn't work, but I'll also leave it as a reminder to myself about the pieces of it that might be kind of repurposed or used for other work. So I've had projects where they didn't really work out initially, but then I ended up using pieces of those projects for kind of other things that did work out. And so the other thing though is maybe the initial goal of the project doesn't work for whatever reason, but you can often kind of like pivot away from it. And so you can kind of use the ideas or the insights you had. So like, well, I thought I was addressing this question, but actually there's another question nearby that, I thought about and I can maybe reuse the pieces I had. So trying to salvage pieces from like, something that didn't initially work is often very fruitful.
Okay,
I try to do a lot of that. Well, yeah, I mean, many of my projects just kind of fail outright. And so I have to think about what I'm going to do with them. So yeah.
Okay. So I have some questions from the people. They send me those questions when I announce this podcast. So let me ask those questions. So the
Okay.
first question is that should students researching in other fields such as nuclear physics or condensed matter physics learn string theory?
Well, I mean, at some kind of like broad level of being like a well-educated person, then I would say yes. But obviously, if you're not researching it, then but there's many ideas that kind of have interesting cross-fertilization. So, I mean, many interesting ideas from kind of quantum field theory kind of apply in different ways, and the motivation for those things comes from different areas, right? So, obviously, high energy theory uses a ton of quantum field theory, but many ideas from kind of condensed matter also inform that. And so, kind of having I would say a broad set of ideas connected with field theory has proven to be helpful. Now, string theory specifically, I mean, it depends on how broad you want to be in even defining what you mean by string theory, I guess. But I would say, it's good to kind of know, it's definitely for sure good to know for other areas about like 2D CFTs, and it's even interesting to know about how 2D CFTs behave on different kinds of backgrounds in geometry. So that at the kind of most qualitative level, but also, techniques from holography, even if you say, well, it's not going to give me the most realistic condensed matter system, it's a different perspective on how to understand strongly correlated systems. So even if it's not directly useful for your particular research project today, just knowing some basic features of how strong coupling works and things like this can be interesting. So I would just say like at a broad level, just as part of like, just general education, I think it would be good. But, I mean, the more specialized things, probably not. But on the other hand, I wouldn't ask like my high energy theory students to be, doing like the absolute like cutting edge versions of certain things in condensed matter. But like I would still want them to know the basics of the field in case like, their interests change or to kind of get motivation from other areas. Yeah.
I see. So the next question is that do you have any advice on learning the topics that are too abstract and hard to visualize?
Uh, any advice? Well, I mean, I think the most important thing is to kind of start building up like a mental model. So if you can't visualize it at all, then okay, I don't know what to, but you can kind of start by kind of stripping away kind of like the kind of most complicated pieces of it. So maybe where the question is heading is like how to think about, I don't know, things like higher dimensional geometry. And there's tricks that people have for example like algebraic geometers, right? When they write a complex curve, they don't literally write like what looks like a Riemann surface or a donut or anything like that. So if they're writing a CP1, they don't draw a sphere or a balloon. Instead, what they draw is just like a line because they're thinking about, well, it's a complex line, and I can talk about them intersecting like this. So this is a way of kind of immediately compressing the data you have associated thing to kind of abstract away from that and visualize what's going on using kind of like a cartoon version of what's happening, but nevertheless an informative cartoon. So so often actually when I'm like reading like either a math paper or a math book, one of the first things I'll do is see if I can kind of build my own mental model of what is going on. Not necessarily the one that they have, but so they give some abstract definition. It's like, well, do I understand what happens if I start playing with the definitions, or if I change this or that? Do I understand what I've changed in terms of the attributes of this object? So I think kind of coming up with your own mental picture is, I think, the most important thing for that kind of more abstract stuff. Uh,
Hmm. Okay. So the next question is that if I ask you about your 2 to 5 minute version of what are the most important problems in high energy physics today, what would you say?
I
In
don't know. So I would say for me at least, the one of the really important questions is to better understand what the space of kind of consistent quantum field theories is and how they can kind of couple to gravity. I think that's actually still one of the kind of big pressing questions. Both at kind of a formal level, but also, just to understand better what is quantum field theory, but also at the level of, potentially phenomenological questions. Like, are there really like complete gaps in terms of things like, a particle phenomenologist wants to do for particle physics and things that just cannot be realized in any way? So I kind of view that as a very kind of interesting big pressing question. And, there's various ways of getting at that, which is, through string theory and so on, in holography, but also, just broadly as like an effective field theory, type class of questions. So that's one kind of general big question. I think another one, which is a little bit out of favor these days, is to kind of think more about, and I have been thinking about it more, is more on like what what things look like microscopically and how like long distance phenomena emerge from it. So I mean, like work on like trying to formulate kind of M theory non-perturbatively, for example. The general question of like what are the kind of the core principles that kind of from quantum gravity produce uh like interesting like long distance phenomena. That's I kind of view that as like one of the kind of big questions like overhanging a lot of things. Then of course there's like, more specific things like about can you really make like scale separated ADS? Can you really make de Sitter? Those kinds of questions. But I have the feeling that like, without having a better like microscopic understanding of some of these things, then it becomes you might even say premature to kind of try to come up with a complete kind of quote unquote no-go theorem for either having or not having such backgrounds.
I mean,
So
both of these things have, swampland conjectures, no scale separation, no
yeah, yeah, yeah,
decision.
yeah, exactly. But again, like you could always say, well, you just looked under the lamppost. How do you know that
Mhm,
there's not some very clever way to do this?
mhm.
And that I think that would require having a better kind of handle on microscopically what is going on. And so uh, Yeah, so I think those would be like the main questions I think is, or those are the kind of the questions that are kind of like animating or motivating like much of what I'm working on. Of course, the way that kind of like manifests itself is in terms of specific research projects heading in that trajectory. But uh, I mean, for example, another one like is just in understanding better holography. How is it that this like quasi-local space-time is emerging from a non-gravitational system? Uh, do we have sharp examples beyond, say, ADS-CFT, or is it kind of going to be more qualitative and limited in these other settings? So I think coming up with good examples along those lines would also be, uh, and I think it's tied again to this question about like how well one understands microscopically what's going on. So
I see.
those would be the things that are motivating me at least. But yeah.
Sure. So the next question is that do you think that theoretical physics is biased towards talent versus hard work?
Uh, no, I think you have to be talented and hardworking. Honestly, I don't think there's a. I mean, I would say there's also a dimension of like, and I find this actually more surprising, how social you are. That actually plays more of a role than I thought. So at least when I started graduate school, like how important it is, like, because you're working with collaborators and how much how well you interact with people at conferences, things like this. That's also a piece of the story. But I don't know if there's like a bias one way or the other for that. I mean, again, there's like a threshold level of talent I think you have to have. Otherwise, I honestly think it's like not going to work. But on top of that, right, you have to be willing to work it very hard, like even if you have that. Otherwise, it also won't work.
Mhm,
And on top of all that, you have to be able to kind of present yourself well. So you have to be able to give a good talk or something like that. Otherwise, you could have the most brilliant idea in the room, but if you can't kind of communicate it or convey it either in a paper or in a seminar in a kind of clear way that somebody else will appreciate, then also it will kind of just be passed over. So I think the combination of these three is all of them are required. And different folks are better at one or the other, but I think there's a lot of all three that actually happen. So yeah.
okay. So the next question, it's about University of Pennsylvania. It says that I read this news that UPenn is reducing the number of graduate students that it will recruit. Is that going to happen in future years as well?
Honestly, I don't know. I don't know how much I'm allowed to say, but I think it's being dictated right now, obviously, by kind of uncertainties with kind of government funding.
Hmm.
And so it'll be a function of what happens with government funding, honestly. So at
I see.
UPenn, for example, a lot of the graduate students are supported both on kind of teaching fellowships, but also on research fellowships. And so basically, like when we go out and we look for graduate students, we have to have a certain amount of funds from the grants to kind of say we are going to support X number of students. And so because of the way that it's set up like that, I mean, some of it's coming through TA shifts, but if we have uncertainties about the grants, then we want to make sure that the people who are already, in the program are well supported and we're able to kind of fully support them. And so, you know, having this level of uncertainty just means that, well, I mean, what would be the alternative? We admit somebody and then we say, well, actually our grants were cut and we don't know for sure what's happening. And it's really being dictated right now by all the uncertainties with, like, it's not really clear like what's going to be funded because I don't think there's like a very coherent policy at the moment. So
I see. Okay, so the last question from the people, it's a technical question. It says that we do know a lot of examples for non-invertible symmetries on different backgrounds. Do we have any examples of non-invertible symmetries on non-geometric backgrounds like T-folds?
uh non-invertible symmetries on T-folds. So I'm going to interpret the question as can you make interesting quantum field theories on such T-fold backgrounds and
Hmm.
can you see interesting non-invertible symmetries arise from that? So the short answer is I don't know. I have been thinking more about kind of engineering field theories on kind of non-geometric backgrounds going in that line. I haven't specifically
Hmm.
thought about T-folds, but in some cases, calling it a non-geometric background is a bit of a can often be a bit of a misnomer because sometimes you can kind of dualize it and turn it back into a geometric background in some cases.
Yes.
And then you can just study all the properties of the system in that geometric phrasing of the question of the setup.
Hmm.
So yeah, I don't know any examples off the top of my head, but at the same time, it is something I've been thinking about. Like we're kind of looking at symmetries on more non-geometric or generated by more non-geometric backgrounds. Yeah.
Okay, so my questions are over. Thank you so much for your time. It was great to talk to you.
Okay. Yeah. Great. Thanks. Thanks for having me.
So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.